I know you live in laptop that's all the desktops in parallel. I've seen people do that, so they get all. No, 20. Like, yeah, they probably have like a couple. You could just really feel them in parallel. That would be funny. Oh, you want help? Prefix. Sure, you gotta split it up. You want it to be like probably like 3 elements. What's the problem about? Oh, okay. Oh, open. Oh. Yeah, so like when you merge these two, which one is gonna stay open? And then how much in between?
All right. Morning, everybody. And we'll continue with our series of lectures on training. Please shut your laptops, the usual good stuff. And let's begin. Now, okay. I assume you're on the, yes, sir, that's okay. So, Adi, what was the last topic we were talking about? Back propagation. Did we actually begin speaking about backprop? So Ryan, what was the last topic we were talking about?
Gradient descent.
Gradient descent. And we were using gradient descent specifically for? Well, what were we using it for? Training what? So what was the point of the gradient descent algorithm part? To calculate the optimum of any given function, right? So here's how we set up the problem. We were given a training set of input-output pairs, and on each input, the network had an actual output, and they had a desired output D. We computed a divergence between the actual and desired outputs on the network. By the way, so can we? Yeah, we'll check this anyway. So we compute a divergence between the desired and actual outputs. The average of these divergences was what we called a loss. And because the input was given, meaning the x was given, the y was given, the d is given, the only thing that can actually influence the loss is the set of network parameters. And so the loss is a function of network parameters, and this is what we were trying to minimize using gradient descent. But is the loss what we actually want to minimize? Then what do we want to minimize something?
We want to minimize the actual expected divergence.
So what we want to minimize is the expected divergence between the true and actual functions. But the best we can do is the loss, which is the average divergence, right? So we're going to spend some time on figuring out how this works. But first, some notation. Can you guys see this? See the slides? We are going to assume that it's a multi-layer perceptron, that information feeds forward layer-wise. Every layer has its own set of parameters, weights and biases. And so to indicate the set or the layer to which a set of weights feeds, we will use a superscript. So a superscript with parenthesis 1 means that these are all weights going to the first hidden layer. The 0th layer is what we will call the input. No, I mean, we're going to call the input the 0th layer, just for notational simplicity, right? And so the weight connecting the ith neuron in the nth layer to the jth neuron in the n+1th layer is going to be represented as W subscript ij. I is the source, j is the destination, and the superscript is going to be n+1 because that is the layer to which it connects. And a similar notation for the bias. Now recap how we did how gradient descent worked. This works for any function that we're trying to minimize. We would start off by initializing our guess for the optimum. And then when we want to minimize it, we keep taking steps against the gradient. And why do we take a step against the gradient? Anybody? Why do we take, yes?
The gradient gives us the direction in which the function increases the most.
So the gradient is the direction of steepest ascent. So you walk backwards because that you assume is going to get you to the optimum fastest. Now to set this up and we keep doing this till our objective function doesn't change very much anymore. So in our setting, our loss is the average divergence over the entire training data. And so gradient descent is going to be much the same. You'd initialize all your parameters, then you'd go through the layers, and then because a gradient is basically a vector of partial derivatives, every single parameter is going to be adjusted against the derivative of the loss with respect to that parameter. And so this means in order to be able to perform this, we need to be able to compute this guy, which is the derivative of the loss with respect to the parameter. And the loss we know is the average divergence over the training data. So the derivative of the loss is going to be the average of the derivatives of the divergences for the individual training instances in the training data. Very simple. And so this means again that the term we want to compute is this one, the derivative of the divergence for any individual training instance with respect to the network parameters. Any questions? Yeah.
If you're already on local limits, would we want to go in the direction of the gradient?
We'll get to that in a later class, right? Okay. So now we're going to continue with this, but I'm going to spend some time talking about calculus. So Dhruv, how do you define if I say y equals f of x, how do you understand a derivative again?
So any change in basically the delta is any minimal change in x, how does it affect your delta y?
But how did we define it in class?
It's in scalar multiplicative of.
It's not necessarily a scalar, but it is a multiplicative term for any y equals f of x. Delta y equals alpha delta x for small enough x. This guy was our derivative. This is all you really need to remember for calculus. Pretty much everything can come from here without thinking too hard. And we'll see how, right? So for any differentiable function y equals f of x, I can write the derivative is defined as the multiplicative term, which multiplies a small increment in x to give you the corresponding increment in y. When y and x are scalars, I can write this as dy over dx. So this, now I can represent using a picture. I can say x influences y. I'm going to call this an influence diagram, right? And so how does it influence it? On this edge, I'm going to write the derivative. So what does this picture really mean? This picture means that for any small, I mean, all of you are familiar with graph notation, so these are easy to understand. For any small delta x, the corresponding delta y is going to be this guy multiplying the weight of the edge. Is this picture clear to you guys? What this picture means, right? So, okay. And so the derivative graph, the edge carries the derivative. And so any increment of the input is going to multiply the corresponding weight of the edge to give you the corresponding increment in the output, okay? So we're going to use this figure again. Now suppose I have a function x, y, a variable y, which is a function of many variables, x1 through xm. Using the same picture, how would what would the influence diagram look like in this case? Anybody? Mara?
You have a vector x.
A vector x, anybody else? Yeah.
For each of the different inputs into y, the x1, the x2, the x.
So you're going to have each of these is going to individually influence y. This picture making sense, right? And so what would the edges contain using the same notation? Yeah.
The individual derivatives.
So this is going to be the partial derivative of y with respect to xi. And so now if each of these x's were incremented by a small delta, using the standard rules for graph combinations, right, computations, what would delta y be in this case? Anyone? Yes.
It's a weighted sum where the weight is the partial derivative.
So this is simply going to be, what comes in through this edge plus what comes in through this edge, the total input coming from all of the edges. And what comes in over this edge is going to be delta x1 times partial y over x1. What comes in through this edge is going to be delta x2 partial y over x with respect to x2 and so on. This notation making sense to you guys? Right, okay. So this is the influence diagram. This is the corresponding derivative diagram where the edges all have partial derivatives as their weights. And so the overall computation is going to be any increment. So delta y is going to be the sum over all coming edges, and any incoming, specific particular incoming edge is going to give you a value that equals the increment at the input to the edge times the weight of the edge. So that gives you delta y equals partial of y with respect to x1 times delta x1 plus partial of y with respect to x2 times delta x2 and so on. So yes?
What does the diagram give you that the formula doesn't?
This is just showing you what influences what. And so and for a small enough increment, then the graph actually tells you how increments in the input are going to change increment in the output. Yes?
So if we think of sort of y as like sort of weighted sum of the different inputs, we could also.
So it's the increment in y is the weighted sum of the increments of the inputs. That's it.
So would we have like a sort of mirror image, like the matrix of the derivatives that we would attach with our.
We're not speaking of matrices. This is just everything is a scalar. This is very straightforward so far, right? Is this picture confusing anybody? Okay, guys at the back, can you shut your laptops, please? Right. So is this picture confusing anybody? No, okay. So now I have a nested function. Y equals f of g of x. Now when I write an influence diagram, we draw an influence diagram, x influences g. G in turn influences y, right? So the edges over here are going to be like so. I have x influencing g influencing y. So this is going to be the derivative of g with respect to x. This is the derivative of y with respect to g, right? So if I wanted to just write this, what would the edge of this term be, right? Now I have a chain, but then as I walk down the edges, the weights of the edges are going to multiply, right? Very straightforward. And so this one is simply going to be the derivative of y with g with respect to x times the derivative of y with respect to g. This making sense to you guys? Right. Which is where the chain rule comes in, right? X influences g, g influences y. So this guy has dg over dx, this y has dy over dg. Now if I wanted to write delta y, a direct relationship between delta y and delta x, delta y is dy over dx times delta x. But then from this edge, delta y is dy over dg times delta g. From this edge, delta g is dg over dx times delta x. So plugging the formula for delta g on the left to this term on the right, you're going to end up with the formula at the bottom, which says that delta y equals dy over dg times dg over dx times delta x, which means that the derivative of y with respect to x is simply the product of the derivative of y with respect to g and the derivative of g with respect to x. This making sense to everybody? Very straightforward. We're going to use this picture again and again. And so it's important that you get this, okay? So now suppose I have something of this kind. Y is a function of many g's, and all the g's in turn are a function of a common variable x. What would this picture look like? Anybody? Someone want to take a guess? Okay. Yes.
One start node, and then many
G's, yeah, and all the G's are going to influence Y. This making sense to everybody again? Right. And those edges are going to carry the derivatives, right? So the edge from Z1 to Y, Z1 is simply, G1, right? So the edge from Z1 to Y is going to have the derivative partial of Y with respect to Z1. The edge from Z2 to Y is going to have the partial of Y with respect to Z2 and so on. So, and the edge from X to any G is going to be the partial derivative of Z with respect to X. Again, is this picture making sense? Guys on Zoom, is this making sense?
Hi, Professor.
Yeah.
Morning.
Yes, it does make sense.
Yes, it does. Yes, it does.
All right, okay. So now, from this picture, if I ask you the derivative of Y with respect to X, what would you say it is? From this picture, what is the derivative of Y with respect to X? Yes?
So like before where we had delta xi times dy dxi, it would now be delta y delta zi times delta zi times delta x propagated for every instance.
So again, if you just look at everything that goes from here to Y, then we just had delta Y equals summation over I, partial of Y with respect to Zi times delta Zi. We've already seen this, right? And now the derivative of Zi, but then we see that delta Zi equals dZi over dx times delta x. This we know, right? Again, this clear to everybody. And so combining the lot, what would we get? So we have delta y is you're going to be summing over all incoming edges. And so you're going to be summing derivative of y with respect to zi times derivative of zi with respect to x times delta x, right? And so if I write it out like so, this is what you get, and which tells you that the derivative of y with respect to x is the sum over all incoming edges of the product of the derivatives along the path from x to y, on that path, right? And so this will tell me that if I write this is, in case I didn't say it very clearly, I can just say delta y equals summation I, partial of y with respect to zi times derivative of zi with respect to x times delta x. That's, if I combine those two, this is what I get, which means that this term here is the derivative of y with respect to x. Everybody clear? Okay.
Hello, Professor.
Yes.
Can you just go to the slide before?
This one? Yeah.
The one before this slide.
So what was the doubt here?
The one before this as well.
The one before this?
There was delta G that I didn't understand. There was a little...
Okay, so I'm just writing Zi equals Gi of x, as you can see on top in the bright yellow. So this is just shorthand notation, that's it. Okay, all right? So this picture makes sense to everybody, right? DL over, so the chain rule, we learned two things. The chain rule, if I have L equals f of y, where y equals g of z, then dl over d with dz is dl over dy times dy over dz. And the second is, if f is a function of many z's, where each z is a function of x, then it's basically a sum over all incoming edges of the products of partials, okay? Partials of derivatives. So here's your first form. We have a lot to cover, so. Okay. So I give you guys only 30 seconds for this. And I think the 30 seconds are kind of up. So the first one, I'm using Pokemons. Who's Corsola? C-O-R-S-O-L-A. Is Corsola here? Corsola's absent, okay. Who's Shroomish? S-H-R-O-O-M-I-S-H. Who's Shroomish? Okay, so what's the answer to the first question? True, thank you. And who is Mantine? M-A-N-T-I-N-E. Mantine is absent?
I'm
Okay.
on Zoom.
Okay, all right. So what's the answer to the second question?
I think it's the first one. It graphically shows all paths through which one variable influences the other.
The second is also true, right? So the chain rule can be derived from the basic rule of derivatives, true. The influence diagram graphically shows all paths and variables through which one variable influences the other. The derivative of the influenced variable with respect to the influencer must be summed over all paths that connect the influencer to the influenced, right? Okay, guys, please shut your laptops to the back, yeah. Right? So this making sense? And so let's go back to our problem for the day. We wanted to compute the derivative of the divergence with respect to network parameters, okay? We're going to use the rules that we just saw. And so I'm going to show this very simple picture of two inputs, two hidden layers, just for illustrative purposes of illustration. And specifically, within each neuron, there are two operations, as you will remember. First, we compute an affine function of the inputs. Then we put that through an activation. So I'm going to separate the two. And then here are all the parameters using the notation that I had earlier, except that instead of having a bias, I just have an extra input that's pegged to 1. And let's also label the other variables. So again, the superscript represents the layer, and the subscript represents the neuron index. So Z1 superscript 1 is the affine value Z for the first neuron of the first layer. Z1 superscript 3 is the affine value for the first neuron in the third layer. Y's represent the output after the activation has been applied to Z. So Y3 superscript, or Y2 superscript 2 is the output of the activation of the second neuron in the second layer. The 2 and the subscript represents the neuron index. The 2 in the superscript represents the layer, right? And now the Y, final output of the network, is compared to a desired output, and we compute a divergence. Our task is to compute the derivative of the divergence with respect to the network parameters. Now, again, what is this derivative? Say, if I wanted the derivative of the divergence with respect to this guy, what do I really mean? The question, what I want to find out is how much a small perturbation of this guy is going to change the divergence. Yes, Jeffrey?
Or the outputs of the neurons in the previous layer, the inputs to the neurons in the current layer.
Yeah. Right, so that's what we mean, right? But then here's how we are going to do this. If I'm going back to our influence diagrams, if X influences Y influences Z influences the divergence, when I want the derivative of the divergence with respect to X, I'm asking how much does a small change in X change D? But for this, I have to work my way backwards. I have to say how much does a small change of Z change D? How much does a small change of Y change Z? I can combine the two to determine how much a small change of Y changes D. And then I have to take a step back. How much does a small change of X change Y? I combine that with what I've computed so far to get the final derivative. So we're going to have to, so here are all the labels. In order to be able to compute this divergence, we will need all of these intermediate variables, right? And so the first thing that we will do is to actually compute all of these Z's and Y's. And so this process of computing the output from the input is what we'll call the forward pass. I'm just going to illustrate it in the slides here. So again, I'm going to say the input is the 0th layer. So yi superscript 0 looks like an output, but it's actually just the input, right? And so again, I don't have an explicit bias. I'm just I have an extra input pegged to 1 to account for the bias. Again, just for notational simplicity, right? And so when I'm going forward, I want to compute all of these z's and all of those y's. And so when I compute it, I'd feed the input, and then if I want the z value for the first neuron in the first layer, this is going to be simply the weighted sum of all of the inputs. Because I'm computing the z value for the first neuron, it's the weight from the ith input to the first neuron multiplying the ith input itself, right? And these are going to be summed up to actually give you the total z, right? So can you turn your phone upside down? If you're looking at the phone, all right. Don't, all right? And
Hi,
so,
Professor.
yeah.
What does those one means? Are them the bias terms for this
Oh,
diagram?
so the red ones are just the extra input pegged to 1 to account for bias. That's all. Okay?
Thank you.
And so any particular z value is just a weighted sum of all of the previous outputs. I can use this to compute the z's, all the z's for the first layer. Then every single z can now be put through the activation function to compute the y values for the first layer. Now, once I have the y values, all the y values for the first layer, I can use all of these y values using the same formula as before. Every z subsequently for the second layer is just a different weighted sum of all of the y's from the previous layer. And then these can be put through an activation to compute the output of the second layer, and so on. I can keep performing this computation all the way till I compute the end of the output of the network. This business of passing an input through the network is very straightforward. Here's the pseudocode for it. I'm going to initialize my 0th layer as just the input itself. Then I step through the layers. Then within each layer, I'm going to go down all the neurons. For each neuron, I compute the z value as the weighted sum of the output of the neurons from the previous layer. And then finally, the y value is just computed by putting the z value through an activation function. Very straightforward. So the forward pass, this is what we call the forward pass. The forward pass is the business of computing the output of the network for any input. We know how to do this. Pseudocode for it. I'll just skip this, okay? Again, I might as well. So y superscript 0 is the input. I'm going through the layers. Within each layer, I'm going through all of the neurons. For each neuron, I'm first computing the z as the weighted sum of the y's from the previous layer, and then putting that through an activation, okay? So now I have computed all of the z's and the y's. And finally, I have the output of the network itself. And we need to remember these because we are computing derivatives, right? And we know that the derivative depends on where the derivative is computed. So when I want to compute the derivative of any particular y with respect to any particular z, I need to know what the z is. That's why we are actually performing this forward pass so that we can find out all the z's and the y's, right? Subsequently, we're going to compute a divergence between the output of the network and the desired output of the network. And then using the principle I just mentioned that you have to go backwards from here towards the front, we will first compute the derivative of the divergence with respect to the output of the network, all the outputs. Then once we have those, we're going to take a step back and compute the derivatives with respect to all the affine terms at the output layer. Take a step back, compute the derivatives with respect to all the weights for the output layer. Then take a step back and compute the derivatives with respect to the outputs of the penultimate layer, the n-1th layer. Then take a step back, compute the derivatives for the affine terms at the n-1th layer, and then back to get the derivatives for the weights. We just keep walking our way backwards because that's the only way we can actually compute derivatives using the chain rule. So we must start at the end and go back towards the beginning. And because we start at the end and go back and work our way backwards, this process is called backpropagation. You're computing the derivatives at the very output and pushing the derivatives backward one step at a time to compute the derivatives for all the variables in the network, right? So, questions? Yes?
Because you're copying the derivatives like the derivatives with respect to like, if to respect to layer backwards, so.
Yeah, because you keep moving things backwards, right? So, all right, let's actually do the math. The math is very straightforward. And I can do this, or one of you can do this for me. Does anybody want to take the risk of coming up here and messing up on the board? Or, okay, I'll do it. I don't want to trouble you. All right. So here's what we do. First, remember that, here's Jeffrey.
Oh, sorry, I wanted to volunteer.
Oh, you wanted to volunteer? Okay, but you're way back there. Anyway, you should be out here for volunteering. So we assume that we know that the divergence function itself is differentiable to begin with. So if the divergence function is differentiable, the derivatives of the output of the divergence with respect to the input of the divergence, it has a standard formula. So which means the very first thing we can do is to compute the derivatives of the divergence with respect to all the outputs of the network, because that's something that we have for the divergence function. So in the first step, we have the derivative of the divergence with respect to all the y's. Now this is what we must push back, right? So let's go back from here. Now I'm going to use a chain rule. If I have L equals f of y, and y equals some g of z, then what is the derivative of L with respect to z? We saw this. This is the derivative of L with respect to y times the derivative of y with respect to z, right? So this is our influence diagram, right? So I can do that. The derivative, I have the derivative of the divergence with respect to the output of the network, y. I must push it back and compute the derivative with respect to all the affine terms z. And so that's straightforward. The derivative of the divergence with respect to z is the derivative of the divergence with respect to y times the derivative of y with respect to z, right? And so this first term, we already have it. We know how to differentiate the divergence. Now what is the second term? The derivative of y with respect to z. That's just the derivative of the activation function itself, computed at the z, right? And so this guy is simply f prime of z. And again, all our activation functions are differentiable, right? But we need to know what the value of z is. We computed the z in the forward pass. And so because we computed the z in the forward pass, we know how to compute this guy, because again, the derivatives for the activation functions are simple formulae. We know how to implement them. And so I can just plug that in here, yes.
Doesn't this also require the divergence function to have to also be differentiable?
Yeah, that's what we said in the last class, right? The divergence must be differentiable, otherwise you're not doing any of this, right? And so at this point, we have the derivatives of the divergence with respect to z. Yeah, yes, Kanpeng?
By saying that we already computed the partial divergence to partial y, and do we mean we already computed it concretely, or we are just saying that the derivative?
So you would have computed it. We just said that the divergence function is differentiable. We have a formula for the derivatives. And so you would use that to compute the derivative of the divergence with respect to the y's.
Okay.
Right? You must compute everything. It has to all be concrete, right? Because you're going to be coding this. And so now we have the derivative of the divergence with respect to z's, okay? The next thing, I must go back. And so using the same rule, I have z is, I want the derivative of the divergence with respect to the weights for the output layer, right? So if I want to say the derivative of the divergence, I just write d with respect to wi j. I'm not writing the superscript, I'm too lazy. This is simply going to be the derivative of the divergence with respect to z j times the derivative of zj with respect to ij, right? This is just the chain rule. And so that's what I will have. The derivative of the divergence with respect to wij is the derivative of the divergence with respect to zj times the derivative of zj with respect to wij, right? And in the process of pushing derivatives backward, this first term has already been computed. So we have this, right? Now, what is the second term? What is the derivative of zj with respect to wij? Now, if you look at this, I'm just going to draw the final layer. So Zj, for this neuron over here, I can say Zj equals summation over all, I'll call this I prime, Wi prime j times Yi, right? So basically I'm summing over all of the inputs, actually Yi prime, right? Okay, so this is what it's going to be. But then let me just pull out this one term. I'm interested in a specific Wij, right? So I can write this as Wij yi plus summation I prime not equal to I Wi prime j yi prime, meaning I'm isolating the one term whose derivative I'm interested in, and the rest of them do not involve Wij, right? So having written it in this manner, what is the derivative of Zj with respect to Wij? What would this be? This is going to be Yi, right? And what is the derivative of Zj with respect to Yi? That's just going to be Wij, okay? Very straightforward. We are not writing anything fancy. Let's look at these. We're going to use these two guys, okay? And so this first term is simply Yi, which means the derivative of the divergence with respect to any weight is the input to the edge for that weight times the derivative of the divergence with respect to the output of the edge. Make sense, right? And so I can use this to compute the derivatives for all of these guys. Now, I'm going to use another rule, which is this term, where if I have L is a function of x through many branches, then to compute the derivative of L with respect to x, I have to sum over all the branches, right? So here, this y influences the divergence. But then it's influencing the divergence over many outgoing paths. Y influences all of the z's. All of the z's influence the divergence, right? And so if I want the derivative of the divergence with respect to y, I must sum over all outgoing paths. And so that's going to be the sum over all outgoing paths of the derivative of the divergence with respect to the z on the path times the derivative of z with respect to y. Is that making sense to everybody? And once again, this second term has already been computed because we already have the derivatives of the divergence with respect to the z's. And what is the derivative of z with respect to yi? That's just going to be wij, right? And so here you have it. The derivative of the divergence with respect to any y is simply the weighted sum of the derivatives of the divergence with respect to the z's. So this looks much like what you would be doing going forward. The affine terms are weighted sums of the outputs. Going backwards, the derivatives are weighted sums of the divergences, or derivatives, right? And so,
Professor?
Yeah.
Is there a risk of vanishing gradients?
So we're not going to be talking about vanishing gradients and such like for a while yet. Okay. These don't trouble us for now. We're just learning how to compute these things. Yes, Jeffrey.
So in the forward path, the z is a weight, the affine value is a weight sum of the inputs. And in the backward path, the derivative with respect to the inputs is a weight sum of the derivative with respect to the affine.
Yes. It's exactly the sum, So it's an affine function going forward, it's an affine function going backward. It's very nice. Okay? Yes?
Sorry, what do you mean by I prime?
So I prime is this, I could have written k instead, right? I'm just lazy. Does that make sense? Yeah, that's all. Okay, so now we know how to compute the derivatives with respect to the y's. And now if I want to compute the derivatives with respect to the affine terms for the penultimate layer, it's simply going to be using the chain rule. It's the derivative of the divergence with respect to y times the derivative of the activation function itself, right? And again, this term has been computed, and this is also available. And just one last term, because I pegged for the bias term, I just have this extra 1. So you're saying that for the bias, it's like the equivalent of saying y equals 1. That's all. So now I can take a step back, and then once again I can compute the derivatives with respect to the weights of the previous layer. And the derivative for any weight is simply going to be the input to the edge carrying the weight times the derivative of the divergence with respect to the output of the edge. Again, very simple, right? For the bias, the input is 1. So again, nothing complex. So now I can compute the derivatives for these y weights, take a step back, use the same formulation to compute the derivatives for y's, take the step back again, use the same formulation to compute the derivatives for z's. For the weights again, I can keep working my way back all the way until I compute the derivatives for the weights of the very first hidden layer. And in fact, you can even compute the derivatives of the divergence with respect to the input itself by just continuing this derivative rule one step back, right? And if you want to perturb or modify the input, then you would use this. So any questions? Yeah.
If the output was a softmax layer, so every Zn is like every other Yn. In that case, would this also generalize for?
The formula still generalizes, right? The only thing that's going to change is how you compute the derivative of the divergence with respect to the z's in the output layer. That's about it, right? And we already saw that if you're using a KL divergence, that's just going to be the error, right? So, and so here is the entire backpropagation algorithm. You'd initialize this by computing the derivatives of the divergence with respect to the affine terms at the output layer, and then subsequently just step back. The derivative of the divergence with respect to the outputs of any layer are simply the weighted sums of the derivatives of the divergence with respect to the affine terms of the next layer. And then the derivative of the divergence with respect to the z's is simply going to be the derivative of the divergence for y with respect to y multiplied by the derivative of the activation function itself. The one extra computation is the derivative for the weights, where the derivative for any weight is the input to the weight times the derivative for at the output of the weight, right? So I can write the pseudocode like so. There's the initial setup on top, but then observe that as you go backward, what you're really doing is computing a weighted sum of the derivatives of the next layer, and then passing this back and multiplying that by the derivative of the activation function, the red. Does this look like the forward pass to you guys? This looks a whole lot like the forward pass. This is, in fact, very analogous to the forward pass. What do we do in the forward pass? In the forward pass, you first compute a weighted sum of the outputs of the previous layer, then you put it through an activation, right? In the backward pass, you compute a weighted sum of the derivatives ahead of you, and then pass it back through an activation. So it's exactly the same operation. The one extra operation is that you're computing the derivatives for weights, right? Any questions? Yeah.
Sure, you're doing this, but can you zoom back out? Like, so after we know the divergence with respect to the outputs, how are we updating weights with that?
So you're going to be plugging that into so you have the derivative of the divergence with respect to the weights,
yeah,
right? And then if I use gradient descent, how did we actually perform gradient descent? The weight itself is going to be updated as the current value minus the derivative times a step, right? That was the gradient descent rule. Yeah. Remember? And so we're just talking about how you would be computing these derivatives. We saw where these derivatives plug into the formulation in the beginning of the class. So this is the forward pass. This is the backward pass. You can see they look very much the same, right? So in fact, when you're writing the forward pass, you can essentially use the same code with very minor modifications for the backward pass. Okay, so here's your second poll. Okay, this is an easy one. Can you give me a Pokemon? Who is this? Whiscash, Whiscash. Who's Whiscash? Whiscash is a person who's. Are you Whiscash? No, you're not. Wishcash, is it? Okay, who is that? Who's Wishcash? Okay, Wishcash is absent. How do you pronounce that? Who's Nidoking? I need my glasses. I can't see that thing.
I'm on Zoom, sir.
Okay, Nidoking, what's the answer to this question?
I'm gonna rock with the third option.
Okay, does everybody agree that the third option is right? Right, backpropagation is the business of computing derivatives. People will often say, I'm training with backpropagation. Are you really training with backpropagation? You really aren't. You're using backpropagation in the gradient descent algorithm for training. Training itself is performed by a different algorithm. This is just a mechanism for computing derivatives, right? Okay, guys, get the back. Please keep your laptops shut. It's very annoying to keep seeing you open them up, all right? Once the poll is done, just shut it up, okay? So this is the correct one. So we've covered a lot, but there's some special cases. We've assumed that each neuron can be individually accounted for, but so the computation of the output of one neuron doesn't affect the computation of other neurons on the same layer. That the inputs to neurons can only combine through weighted summation, they're affine, and that the activations are differentiable. Now, all of these can be violated. We'll look at some special cases, right? The other cases are also discussed on the slides. Just look them up, they'll appear in the quiz. So we've already seen a case of a kind of activation where changing the input to one neuron changes the outputs of all the neurons. We call that vector activations, right? So in the case of scalar activations, if I change any particular weight, that's going to change one z. Changing one z is going to change one y, right? Whereas in the case of the vector activations, if I change a single z, all the y's are going to change. And so if I draw the, write it out, in the first case, every y is a function of just that corresponding z. In the second case, I have to consider the set. The vector of y's is a function of the vector of z's. And changing any z can change any y, right? So if I were to draw the influence diagram over here, in the first case, each y is only influenced by the corresponding z. In the second case, every y is influenced by every single z. And so, this making sense? And so when I write derivatives, right, over here, in the first case, I have all of the z's, z1, z2, z3. These influence their corresponding y's, y1, y2, y3, and these finally influence the divergence. So if I want the derivative of the divergence with respect to any particular z, I just need to compute the derivative of the divergence with respect to y, and then multiply that by the derivative of y with respect to z, right? So this is very simple for the scalar activations. Now if I have vector activations, things get ugly, because every z influences every y. And so now if I want the derivative of this divergence, say with respect to this z, I have to consider all paths going to the divergence, right? So which means that I have to sum over all of the y's, the product of the derivative of the divergence with respect to y, and the derivative of y with respect to z. So this kind of activation is mostly seen in the output layer, typically a softmax, right? So in a case softmax, you exponentiate the z's and then you normalize them to sum to 1. So now we saw that I have to actually use this formula. The derivative of the divergence with respect to any z has to be summed over all of the y's, right? And we already have if I'm backpropagating, I have the derivative of the divergence with respect to the y's. I need the derivative of y with respect to z. And so what does that formula look like? So for the case of the softmax, again, for z, in the case of the softmax, if I have something of this kind, we had discussed this in the last class, right? I have z1, z2, z3, say. So y1, y2, y3. what is the sign of the derivative of y1 with respect to z1? Come on, guys. We discussed this in the last class. What was it?
They are opposite.
If does increasing z1 increase y1? So what is the sign of the derivative? It's going to be positive, right? So what is the sign of the derivative of y3 with respect to z1? It's going to be negative because increasing z1 will decrease y3, right? And so here's what the actual formulae look like. So the derivative, you see yi times 1 minus yi. When you're far away, the derivative is going to be 0. When you're in the middle, it's going to be maximum for the yi. So for the straight path, the derivative is positive. For the cross path, the derivative is negative, and it's simply the product of the y's. And so I can just plug that in. Yeah.
How exactly is this process different from what happened in the previous layer? Is it just because of the uniqueness of softmax, or?
So this is true for any vector activation. This formula is specific for softmaxes, okay? And I can actually have a shorthand notation for writing it. We'll skip this. So we looked at activations, vector activations. We look at some more special cases, right? And so what special cases can we look at? Over here. Another one where you have non-differentiable activations. So here are a couple of non-differentiable activations. One is a ReLU. The other is, so the ReLU is this got a hinge. Do you find a location where you can't compute define the derivative? Where is it? Right at the corner, right? What about the max? Okay, we'll get to the max later, okay? The max is also looks very much like a ReLU. It's a special case of a ReLU. It's a multifunctional ReLU. So in this case, we have a point where the derivative is not defined. So how can we use this? Now, what was the purpose of computing a derivative? Why did we want to compute a derivative? Say that loud? Gradient descent. But why did we want the gradient in the first place? Can you say that aloud, please?
To be more accurate.
To be more accurate. You wanted to find a direction where if you walked in that direction, the value of your objective would go down. That was the only reason we wanted to compute the derivative, right? And so the reason we chose the gradient is that that is the direction where it goes down fastest. But then if I cannot differentiate it, what is my alternative? I find some other direction where walking in that direction will decrease my objective. And so that's all we really do, right? So in these cases, there's something called a subgradient or a subderivative. A subderivative is any direction where, regardless of the size of the step, if I take a step, the function will increase, right? And so, or you just take a step, you find a subderivative, and then I take a step against the subderivative. There can be many such steps, right? So for differentiable functions, the subderivatives are the same as derivatives. Now, this is kind of an ugly definition. So there's a slightly different way of looking at it. Let's look at the ReLU, right? So at the hinge, if I move the z further to the left, if I take a step backward from 0, will it change the output? Yes or no? Okay. So what is the derivative coming from the left? 0, right? If I take a step forward, will it change the output? Yes or no? And what is the derivative there? 1. So to the left of the hinge, the derivative is 0. To the right of the hinge, the derivative is 1, right? But then there's a different way of viewing this. You can think of this as the function rotating from the horizontal to the vertical, to the 45 degrees in one continuous motion, all at one spot. Which means what, if I think of it this way, what is the derivative at that corner? Any value between 0 and 1 is valid because in the process of turning, it has hit every one of these derivatives, correct? And so I can choose any one of these derivatives at that corner. Typically, I'll choose the 1 because it's the largest, but it's a nice way of viewing the problem. That making sense to you guys? Right? And so that's what you would use for a ReLU. Typically, you'd say the derivative is 0 for negative z, and for positive z, including at 0, the derivative is 1. Okay, yes?
So Professor, like, what does the 45 degree, like, I didn't understand the relation between the 45 degree and why was that brought?
So what is the rectified linear unit? The rectified linear unit just copies the output for positive inputs and then thresholds it for negative inputs. So that's a 45-degree line, right? Y equals X. Right, yes, referee.
So the idea is that the transitions from like a flat line, because like everything, like if X is less than 0, the output is 0, to like a straight line, which usually has like a derivative of 1. But the thing is like the transition spots X equals 0, and the derivative of that transition spots it has to be between 0 and 1. It can't be say like 2, because like
then you'd be exceeding it, right? So any point, anything between 0 and 1 is valid. So that makes sense to everybody? Right. So another activation function is the max. So let's say I have something of this kind, you know, y1, z1, z2, z3, where, and just say z1 is 1, z2 is 2, z3 is 3. And then y equals max of these guys, okay? So what will the value of y be over here? In this case, if z1 is 1, z2 is 2, and z3 is 3, what is the value of y? 3, okay. So if I perturb z1 by a little bit, will y change? So what is the derivative of y with respect to z1?
0.
If I perturb z2?
0.
If I perturb z3? 1, because any perturbation of z3 is going to result in an instantaneous change of y. Yeah.
What if Z1 and Z2 are very close and the perturbation actually...
It doesn't matter. You're looking at such infinitesimally small perturbations. Unless they are identical, it doesn't matter. If they're identical, then both of them will have the same derivative, right? Okay. So in this case, the derivative of z, y with respect to z is 1 for the largest value and 0 for the rest of them, right? And so here's a point.
Excuse me, Professor.
Yeah.
If both Z1 and Z2 are equal, the perturbation of either one is not going to change the output or the max function.
So for both of them, the derivative would be 1, right? So when you have, when the maximum multiple values hit the max, then all of them have a derivative of 1 going forward. You can actually choose any value between 0 and 1, but we typically use 1. Right. Okay.
I don't see the poll, Professor.
You don't see the poll?
I see it.
Okay. All right. So where are my glasses? I need my glasses to know who's going to answer. Who's Duskull? D-U-S-K-U-L-L. Is that how it's pronounced? Duskull. Duskull's absent. Okay. We're going to post all of, all of these. Who's Marie?
Duskull is here.
Okay, Duskull. What's the answer to the previous question?
The second choice and the fourth choice and the fifth choice.
Right. So Z1 is not the maximum, so the derivative is 0. Z2 is not the maximum, the derivative is 0. Z3 is the maximum, the derivative is 1. The rest of them are, 0, right? So very good. Wrong. Anyway, questions so far? Yeah.
In the case of the subderivatives, so there are infinitely many that we could take. How do you decide between, like conceptually?
You can pick any of them. So typically we would take the one that increases fastest because we are interested in speed, right? And so here's the backward pass. These derivatives here, dy over dz, can be subgradients. That's about it, okay? And so the overall approach, when you have training data, you perform, for each data instance, you perform a forward pass. You pass the instance through the entire network to compute all intermediate variables and the output. And then you perform a backward pass, which is back propagation. You sweep back, you push the derivatives backwards through the network to compute the derivatives with respect to all the parameters. This backward pass is actually computing the derivative of the loss, which is the average divergence over the training data with respect to all network parameters. And so once you compute this derivative of the loss with respect to the parameters, to answer your question, Jason, now you can just plug that into gradient descent, right? Questions? Okay. So I have the pseudo pass code for the whole thing. There's a forward pass and a backward pass, right? So we went through the easy bit. But now let's do it. Let's look at how you would actually do it. You would never write code the way I just showed it on the slides, because that's going to be tremendously slow. These days you use GPUs, vector processing. So everything is going to be a vector or a matrix. And the whole thing can be formulated as vectors and matrices. How many of you are fully comfortable with vector calculus? Okay, that's because you went to the Putnam. Anybody else? No, okay. You don't have to win the Putnam Prize to understand vector calculus. It's actually very easy. So long as you can draw a line and put a weight on top of the edge, everything just works out. And we'll see how, okay? So for layered networks, it's simpler to think of the process of a forward pass and backward pass in terms of vector operations. And so the arithmetic is simpler. You can use matrix and vector libraries, and the computation is also much, much faster that way, right? So let's see how we can do this. Consider a layer of this kind, right? So here I have a bunch of z's, a bunch of y's, y say, I'll just write this y1 through yn, and these are used to compute a bunch of z's. And let's say these are z1 through zm. So the number, you can have more neurons in the next layer, right? So if I write this out, then let me put all of the z's in a vector. So I can say z1 through zm. Let me put all of the y's also in a vector. So this is y1 through yn. Then I can write a matrix out here where the first row of the matrix represents the set of weights going into z1, right? So this is w11, w12, w1n. So the second row is going to be the set of weights going into the second neuron. Yes?
Maybe w21 instead of 1, 2.
Thank you. You're right. w21, right? And 1. I always get confused. The second row is going to be the set of weights going into the second neuron, okay, which is going to be w12, w22, wn2, and so on, okay? Plus, I can write a vector of biases for each of these guys, b1 through bn. And you can see that the math works out, right? So z1 is simply going to be w11 y1 plus w21 y2 plus w31 y3 all the way to wn1 yn plus b1, right? This is exactly the scalar equation written in matrix form. And so I'm going to use k as a subscript to represent the layer number in this case, just for convenience again. There's a bit of switch of notation. And so I can just write zk is wk yk minus 1 plus bk. And similarly, now I can say the activations are a vector operation, which operate on the vector of y's to z's to give you the corresponding vector of y's. Is this making sense to everybody, the way we've written this? And so once you write this in matrix form, you can see that this is exactly the same as what we had earlier. And this can now just be used for your forward pass. Again, I can say y0 is my input. The first thing you would do is to compute your first half set of vector of affine values, which is w1 y0 plus b1, right? And then once you've computed all of these affine values, you're going to put them through the activations to get y1, which is just the activations of the first layer operating on the vector of z's. And then subsequently, I can compute the z's for the second layer, which is just w2 y1 plus b2, right? Weight times z's plus bias. That's the affine function, right? And so that gives me the affine vector for the second layer, which I can put through an activation. And so I get the y's for the second layer, right? And then I can just keep doing this till I finally get the affine values for the final layer, and I put it through my activation function, and I get my output. So very, very straightforward. And so if I actually write the pseudocode, this is so much cleaner than what we had for the for where we wrote out the individual variables explicitly, the scalar representation. I can just define my weight matrices for each layer. And then as I go through the layers, I just say y0 is the input. The affine vector zk is simply wk times by k minus 1 plus bk. It's an affine function of the y values for the previous layer. And the y values for any layer are just computed by putting this affine vector through an activation. Any questions about this? And yes?
Are we just doing computation element-wise?
So this operation, yeah, I mean, how you implement this, you could implement this element-wise, but then, if you're working with an NVIDIA GPU, they're going to do the matrix operation where all the operations are done in parallel, right? So it gets abstracted out. It's just it's a vector level operation. And that abstraction really helps because you have so many vector and matrix libraries. Yes?
Really, let me example, sir. So basically, like, is the weight matrix, right? So the first row of the weight matrix, I believe, is the weight of each input into like the first neuron.
Yes.
So, basically, like, we have no like the first row of the weights with like the column vector of the inputs, and that gives us a weight sum of the inputs into like the first neuron, which is obviously the affine of the first neuron.
Yeah, absolutely. Yeah, plus the bias, but yeah, that's about it. So, any questions, guys? Any doubts? Okay. You better be yes.
There is no change in this formula if y is the output, y vector is not a vector. Like you have a binary classification.
So when we perform binary classification, we just use a sigmoid activation or a softmax activation, but the activation function is still a vector operation, right? Y equals f of z.
So the final y, whether it is vector or the final output.
The final output is still a vector. You would be computing a probability distribution, which is computed by applying a softmax to the z's, right? So if you want to perform classification, you're going to say y equals softmax z. This is a vector, this is a vector, this vector is going to be a probability distribution. That's it. Okay, all right. So this is good. The forward pass. Look at the code. It's so much cleaner, right? Much easier. I just say z equals an affine function of the y's, and then I add a bias. I put it through an activation. So the real fun happens when you begin looking at the backward pass. This is where all of the vector calculus kicks in. Yes?
In this zero code, where would the v store the gradient?
There's no gradient here yet. This is just the forward pass. We are not computing gradients yet. So that's the backward pass. That's the fun stuff. It turns out that that's actually kind of easy. And I'm going to present some more calculus, but this time it's vector calculus. Let's see how. So let's say I have a scalar function y of a vector argument z, right? Y equals f of z, but z is now a vector. I can still write so again, according to our derivative rules, we said delta y equals the derivative of y with respect to z times delta z. Assuming z was a column vector, what was the derivative of y with respect to z? It was, can you say that aloud? I can't hear you guys. Can you say it aloud? It was a row vector. What were the entries of the row vector? The partial derivatives of y with respect to z's, right? But then, and the transpose of that was the gradient. But I can still draw this influence diagram. Z influences y, and the derivative is the derivative of y with respect to z. And once I write this influence diagram, then that formula still holds, right? Delta y is the derivative of y times delta z. Make sense? Okay. So now, that was for a scalar function of a vector argument. What if I have a vector function of a vector argument? Y is also a vector. Now, when y is a scalar, so when y was a scalar, you said delta y equals partials of y with respect to z1 times delta z1 through delta zn, right? This was easy for when y was a scalar. If y is a vector, what is a vector? A vector is just a vertical stacking of scalars, correct? So I can just write this as delta y1 equals delta y2 equals, again, the same thing, partial of y2 with respect to z1, partial of y2 with respect to z2, and so on. Right? And so the whole thing now just becomes this. Now that vertical stacking of derivatives becomes a matrix. That matrix is called a Jacobian. Right? There's nothing magical. Our formulation didn't change. Delta y still equals the derivative times delta z. Make sense to everybody? Right? Nothing changed. This is the beauty of it once you begin saying things this way. And so we can write this. I like that there's the Jacobian notation where I put the g, j, but I just want you to remember that it's a derivative, right? So everybody clear with this? And so now if I have a set of scalar activations, the set of scalar activations is still can be thought of as a vector activation where there's no cross interaction, right? Which means the partial of any y with respect to the z's that are not itself are going to be 0. So the Jacobian matrix is going to be a diagonal matrix. Whereas if you have a proper vector activation where every y is influenced by every z, then the Jacobian matrix is going to be a full matrix. In the case of a softmax, this is going to be a full matrix. Everybody good so far? Okay. So let's look at some special cases. Special cases, let's say I have an affine function. Again, z equals wy plus b. Now I want to compute the derivative of z with respect to y. Yes, Jeffrey?
Does the Jacobian or the softmax end up being positive on diagonals matrix elsewhere?
Pretty much, exactly, right? And so now, if I have this, if I want to compute the derivative of z with respect to y, what am I saying? I'm asking how much, what do I have to multiply a small increment of y by to get the corresponding increment in z? So let's say I increment y by delta y plus b, right? This results in a small increment in delta z. So you can see that wy plus b is the same as z. So this gives you delta z equals w times delta y, which means the derivative of y with respect to z is going to be w. That's the Jacobian of z with respect to y, right? Similarly, if I perturb b by a small amount, z is going to change by the exact same amount. So the derivative of z with respect to b is an identity matrix. Everybody with me? Okay. Now the chain rule, if I say y equals, y of z of x, x influences z, z influences y, right? So again, if I write the chain rule, the derivative of z with respect to x is on top of the first edge. The derivative of y with respect to z is on top of the second edge. And so the derivative of y with respect to x is the derivative of y with respect to z times the derivative of z with respect to x. Very easy to show that this is the case. Delta y is derivative of y with respect to z. Delta z times delta z. Delta z is the derivative of z with respect to x times delta x. So plugging this over here gives you delta y is the derivative of y with respect to z times the derivative of z with respect to x times delta x. So if I think of delta y as a function of delta x, the multiplicative factor is the derivative of y with respect to z times the derivative of z with respect to x. Right? Note the order. The outermost edge went first. And then as I walk backwards, I'm right multiplying. This makes sense to everybody? Right? So now, okay, this good? Any questions? No. I'm going to use this. So now suppose I have something. X influences z1, influences y1, influences z2, influences y2, influences d. Right? How do I compute the derivative of z with respect to, say, x? Here's what I can do. First, d is a function of y2. So the derivative of z with respect to y2 is just, the nabla d y2, right? Now then, if I want the derivative of d with respect to z2, so so that is, the nabla d z2. Just looking at what happened above, you can say that the derivative of z with respect to d2 is the derivative of z with respect to y2 times the derivative of y2 with respect to z2. I just write multiply. Making sense to everybody? Right, and so I got this. Now what is the derivative of z with respect to y1? The derivative of z with respect to y1 is the derivative of z with respect to z2 times the derivative of z2 with respect to y1. Right? Straightforward, as before. And so what is the derivative of z with respect to d with respect to z1? The derivative, that's the derivative of d with respect to y1 times the derivative of y1 with respect to z1. It's always right multiplying. And at each point, notice that the term that's in blue has been computed in the previous step. Right? As I keep going backwards. So I can go all the way back to the beginning. Is this making sense? How I actually compute the derivatives and why this is a very trivial operation. Right? And so now there's and so this is the extended chain rule. If I want the derivative of d with respect to x, I just keep right multiplying as I walk backwards through the chain, so long as I can draw the influence diagram. Okay. One final bit, if z equals wy plus b and d is f of z, that's the influence diagram on top, then the derivative of d with respect to y is the derivative of d with respect to z times w, because w is simply the derivative of z with respect to y, right? Easy. But then here's the crazy bit. The derivative of d with respect to b is the derivative of d with respect to z times the derivative of z with respect to b. The second term is an identity matrix. So that's just the derivative of d with respect to z. The third one is a little more complicated. So this is something, because you're taking the derivative with respect to a matrix, things change a bit. It gets a little funky. It's easy to prove, but I'm not going to prove this in class. But if I have z, y influences z through a w which influences d, then the derivative of d with respect to w is going to be y times the derivative of d with respect to z. Okay, let's see how this works by checking sizes. So let's say d is a scalar. This is 1 cross 1. So let's say z is an n cross 1 matrix and y is an m cross 1 matrix. What is the size of w? Anybody? If d is n cross 1, z is n cross 1, and y is m cross 1, what is the size of w? So w is going to be n cross m. Okay. Now we said something in the previous class. The derivative of a scalar with respect to any object, vector or matrix, is going to have the same shape as the transpose. Right? So when I take a derivative with respect to a row vector, it became a column vector, it became a row vector. If I take a derivative with respect to a matrix, it becomes a transpose of the matrix. So let's check the size, right? So what is the derivative of d with respect to z? What's the size? Yeah.
Is that 1 cross n vector?
So this is going to be 1 cross n, right? And what is the derivative of z with respect to y?
1 cross n.
This is a matrix, that's w, right? That's going to be n cross m. Is that right? No. No, z. Actually, no, what is y? The size of y is m, right? M cross 1. So the product of these two is m cross n. So when I multiply y with the derivative for z, it's m cross n, which is the same as the size of the transpose of w. So that's how these two equations work, okay? And so now we've got all of this, right? So if I have z equals wy plus b and d is f of z, the derivative of d with respect to y is the derivative of d with respect to z times w. With respect to b is the derivative with respect to z. With respect to y, with w, it's y times the derivative with respect to z. And the shapes work. And now, Let's apply this to neural networks. I'm going to go over a couple of minutes, guys. Please bear with me. It doesn't take long once you set this up, okay? So here is a typical layer of a network. Y is used to compute Z. Z is used to compute the next Y. Those Ys are eventually going to be computing the divergence. So here is, I'll skip this poll, okay? No time. Here is a complete neural network. If I write down, so here are all the variables. X going in, then there's a Z, then there's a Y, then there's a Z, then there's a Y, all the way to the final Y. And then finally there's a divergence. So if I draw the influence diagram, this is what it's going to look like, right? And so the variables are shown. X influences Z1, Z1 influences Y1, Y1 influences Z2, Z2 influences Y2, and so on. And now I can write down the derivatives on top of the edges. I'm using the inverted triangle, the nabla, to show derivatives, okay? So here are all the derivatives. Each edge is showing the derivative of the output with respect to the input. Okay, so what are these guys? Well, this edge which shows y as a function of z, what is the derivative? Those are activation functions, right? So what are those derivatives? Those guys are just the Jacobians of the activations, correct? And then what about these guys? What is the derivative of z with respect to y? Those are just the weights, correct? And so now I have the entire chain. I know exactly how to perform backpropagation at this point. We've already seen this. I start off over here. I already have the derivative for y. To get the derivative for z, I just multiply that by this new term, which is the Jacobian. Then to get the derivative for, right, then to get the derivative for, so now we have the derivative for z. Then to get the derivative for w, for y, I'm just going to multiply that by the derivative on the edge, which is the weight matrix, right? And then one final thing, we also saw that if I want to compute the, so that's a new term. And then if I want to compute the derivative for the weight matrix and the bias, we just saw that if you have anything of this kind, y going to z going to divergence, with the w, the derivative for this is y times the derivative of the divergence with respect to z. So the input times the derivative for the output, right? And so that formula is already written over here. We know the derivative for b. And so now I've taken a step back. It's just three little formulae, right? And then I can keep following this computation all the way back to the beginning of the chain. So when I write it in vector formulation, it's actually very simple. I can just start off, initialize by computing the derivative for the z's. And then at each point, as I keep walking back, I first multiply by a Jacobian, then I multiply by a weight. Then I multiply by a Jacobian, then I multiply by a weight. And that's all I do, going backwards. The one-off is computing the derivatives for the biases, which is simply the derivative with respect to z, and for the weights, which is the outer product of the input of each link, and the derivative for the output of the link, right? So I have the whole thing in pseudocode over here. So just to wrap up, I went a little bit over, I apologize. Go through the slides, guys, right? The math is very, very, very simple for backprop once you write it in vector formulation. So here's what you'd be doing if you were training. You'd be given a bunch of training data. For binary classification, the labels are binary. For multi-class, you'd be given the class index, right? You'd be setting up your loss function, computing derivatives using backprop, plugging the backprop into gradient descent, and then you'd compute your update your parameters, right? So neural networks must be trained to minimize the average divergence of the output of the network and the desired output. Minimization is performed using gradient descent. Gradients can be computed using backpropagation, which have a forward pass and a backward pass. And these can be incorporated into gradient descent. Thank you. So final thing, will this actually learn what you want it to learn? How well does it generalize? What does the output mean? We'll see this in the coming classes. Thank you.